This screencast will cover Section C of the topic for Cycle 2 Apply Lab, tables 2 and 3. In the first screencast, I found that the spring constant for the rubber band was 150 newtons per meter, and I'll use that for all of the rubber band stretches. You might find that it's not that linear in some sections. There might be a little bit of an issue on the measurement, but use that single value as you go through these calculations. So in this section, Table 2, we're going to calculate the elastic potential energy at each of the stretches listed. Depending on what you're doing, there may be 5 or 6 entries. This one just has the 3. Okay. Remember that the formula for elastic potential energy is equal to 1/2 k x squared. K is our spring constant listed here, and x is the amount of stretch. Let's do the sample calculation for 0.02 meters. That's the same as 2 centimeters. So that'll equal 1/2 k, 150 newtons per meter, and our x, 0.02 meters squared. Now it's going to be important to remember PEMDAS to do our square operation before we do the rest of the calculation. So that you see the full effect, I'm going to go through this full calculation. 1/2 times 150, that would be 75 Newton meters. Now 0.02 meters squared is going to be 0.0004 meters squared. When I multiply this out, I get 0.03 joules. You can probably see that I get Newton meters. I have meters squared. It'll cancel with one of those. I get Newton meters, which is the same as a joule. So this would be 0.03, and the joules is already written. That's a pretty reasonable value. Now for 4 centimeters, that's the same as 0.04 meters. I multiply this out and I get 0.12 joules. And for 5 centimeters, likewise, I get 0.1875. I'm going to round that to 2 decimal places. 0.19 joules. I'll fill that in the table. 0.12 joules, 0.19 joules. These would be pretty reasonable values. You probably see something fairly close to these, anywhere from maybe 0.02 to maybe 0.2, depending on your spring. Now, Table 3 asks us to predict the speed and the height that we'll end up getting for our car based off of the amount of energy we had stored in our rubber band. Okay, so first thing would be we just end up transferring the elastic potential energy from Table 2. When you type this, obviously this will go away. I'm going to be writing it, so I'll have to write over the top of that. Let me fill that in now. So I've just transferred the values from the previous table. The car and marble mass for all of us, unless you ended up putting too many marbles in there, should be 0.10 kilograms for all of these. From speed, what we're looking for here is if I took all of this elastic potential energy and it became kinetic energy, how fast would the car need to go? And let's take a look at the equation that covers kinetic energy. So if all the elastic potential energy became kinetic energy, and our equation for kinetic energy is 1/2 mv squared, how fast would we have to go? I'm going to use the case for that second entry here, 0.12 joules. 0.12 joules of elastic potential energy became kinetic energy. How fast would that need to go? I'm just going to do it for that one case, and we'll find out what we get. Okay, so I'm going to change this around, so I'm going to isolate the speed or velocity. So I'm done with the algebra. I say that velocity is going to be equal to the square root of 2 times our kinetic energy. Remember, that's the same as our our elastic potential energy over here, divided by the mass. Let me go ahead and figure that out right here. I can see this works out to be the square root of 2.4. It'll be meters squared per second squared. When I take the square root of that, I get 1.5, 1.55 meters per second. That's how fast I would expect it to go. 1.55 meters per second. I can do those for the other values. Let's take a look at the expected height here. So if all of the elastic potential energy became gravitational potential energy, and gravitational potential energy is mass times gravity times height, we were looking for the height. I could just isolate that, rearrange this. H is going to be equal to our gravitational potential energy times mass times gravity. So in this case, let's go ahead and finish this off. I have my 0.12 joules divided by the product of 0.1 kilograms times 10 newtons. I get 0.12 meters, same as 12 centimeters. And remember, that's how far up that goes. So I would know that this should be 0.12 meters. Remember, these are our predicted values. As we move to table 4, we'll see what we actually measured for our car.